Let's get into our content for today. So, let's start with vectors and projectile motion. So, we'll deal with vectors a lot in both topics 1 and 2. They're really an important part of Year 12, so you need to make sure that when you're learning them, you understand, especially the vector resolution. So, a vector is a quantity which includes both direction and magnitude. Alright? So instead of just being, say, 5 meters per second, a vector quantity would be 5 meters per second to the right. So it has a direction as well as a magnitude. The opposite of a vector quantity is a scalar quantity, and a scalar quantity only has magnitude. So a scalar quantity might be something like 5 kilograms, alright, because there's no direction there. So, there are a few different ways that we can represent vectors. The first way is just by writing it down, 5 meters per second to the right, or alternatively, you can also draw them as arrows. So, when you're drawing a vector as an arrow, the length of the arrow represents the magnitude of the vector, and the direction of the arrow represents the direction of the vector. So, as an example here, our vector 5 meters to the right might be represented by this vector along the bottom here if it had a length of 5. So, the most common example of when you'll see vectors in Unit 1 is looking at projectile motion, and we'll get into an example of that in a second. But the other thing that it's important for you to understand about vectors is that they are also important to use, especially when you get into electromagnetism. And that's because when you get into electromagnetism, we talk a lot about electricity and magnetic fields and that kind of thing. And you need to be able to resolve vectors using those in those contexts. So make sure that you do hold on to these vector skills because they are relevant later in the year as well. Alright, now getting on to projectile motion. So, a projectile is any object that's kind of thrown. Alright? So, it can either be thrown from the ground, alright, such as somebody kicking a ball or somebody throwing a ball, or it can be shot, maybe a person firing an arrow, or a cannonball shooter, or something like that. So, we have an object being shot with an initial velocity u, so we denote that as u, and then it will curve through the air subject only to gravity. Alright, so this is an important concept to remember. So, when a projectile is being shot, we actually kind of ignore the effect of air resistance, alright? So, you might ordinarily think that something being thrown in the air would be subject to air resistance, but in Year 12 physics, we don't really talk about that too much because it's a little bit too difficult to consider. The equations are a little bit too complicated, so we don't worry about that. But we do worry about gravity. So when you're talking about projectiles, gravity is the only force which is affecting the projectile at all. And of course, gravity only acts vertically, alright? It acts up and down. It doesn't act side to side. So the only acceleration that you'll see when we're going through projectile motion is vertical acceleration. Alright, and that has a few important effects that we'll get into later. So, projectile motion consists of separate horizontal and vertical velocity vectors. Alright, so when an object is moving, when it's being projected, it is acting vertically, like it's going up and down, and it's also going side to side, which means we have separate horizontal and vertical velocity vectors. Something that you need to remember that's mentioned explicitly in the syllabus is that these two vectors are independent. So the horizontal and vertical velocity vectors are independent. Alright? So as I was talking about before, the only acceleration that we worry about in Year 12 physics is gravity, and that only acts vertically. So we don't actually have any acceleration occurring horizontally, right? So what that means is that the horizontal vector, the horizontal velocity vector, will always be the same, but the vertical velocity vector will change. Alright. Now we need to get on to solving some problems involving projectiles. Alright. So there are a few formulas on your formula sheet that you need to be aware of. And I've listed a few of them here. So we have V equals U plus AT, and S equals UT plus half AT squared, and V squared equals U squared plus 2AS. So it's important to know the meaning of all of these letters in these equations. So V is most generally described as the final velocity, or like the velocity of the projectile once it hits the ground. But it can also describe the velocity at any point during the flight other than the beginning. U is the initial velocity, so that's the velocity of the projectile at the beginning of its flight. A is the acceleration, and T is time in seconds. S is the displacement. Alright? And then U, of course, is our initial velocity. And that is all of our variables for those equations there. So, now let's get into a few examples here. So, for this example here, we have an arrow being shot at 40 meters per second at an angle of 45 degrees above level ground. So the first thing we're going to do here is we're going to identify which of these values this information correlates to. So it's being shot at 40 meters per second, which means that our initial velocity is 40. It's being shot at an angle of 45 degrees above level ground. And that tells us that our theta value is 45. So theta is the angle at which the projectile is being shot at. So, the first thing we need to do is draw a diagram showing the trajectory and initial velocity vector. So, as we can see here, we have our level ground, we have the path of our projectile. Path of the projectile is always that of a parabola, so that isn't necessarily a perfect representation. And then our initial velocity vector would be, tangential would be a little bit like that. Alright, so part B is to calculate the horizontal and vertical initial velocity of the arrow. So this is something that's really important to know how to do. Alright? It's really important that you understand this and that you memorize this, because this is something that you will almost definitely come across in an exam or an external. So, calculate the horizontal and vertical initial velocity of the arrow. What this means is it's asking you to consider the initial velocity of the arrow and figure out what part of that is horizontal and what part of that is vertical. So what you need to do here is what we call vector resolution. We're going to draw the initial velocity u, which is 40. And then we're going to draw the vertical and horizontal components. So this will be the horizontal component, and this will be the vertical component. Now we're going to label. So this will be u, and because it's horizontal, it would be in the x direction, and this will also be u, but because it's y, be in the y direction. Alright? The other thing that we know is the angle at which the arrow was shot at, which was 45 degrees. So, whenever a question asks you to find the vertical and horizontal components of the initial velocity, what you need to do is draw the initial velocity along with the vertical and horizontal components, labeled uy and ux respectively, with the initial starting angle. From here, we can use the sine, cos, and tan ratios to figure out the ux and uy values. Right? So, uy is going to be equal to u sine theta, and ux is going to be equal to u cos theta. Now make sure that you remember these two formulas because they are important. You can of course just get them from looking at the triangle, but what you'll tend to find in a lot of cases as you tend to practice more questions is that you stop drawing the triangle and you just start using the formulas. So make sure you do remember those, and they're not on your formula sheet. So subbing our values in, we're going to have 40 sine 45 and 40 cos 45. So if anybody is in methods, you might know what sine of 45 and cos of 45 is, right? So we're going to have our initial velocity in the y direction will be 28.28 meters per second. And of course the direction of that would be upwards. And then 40 cos 45 is the same thing. So this allows us to find the vertical and horizontal initial velocities. So something that you might notice here is that our two vertical and horizontal velocities are actually the same value. This isn't surprising because our angle is 45, and as I said, if you're in methods, you might know why that is. But something to keep in mind, and this is not something that's explicitly mentioned on the syllabus, but just might be something that comes in handy, is that the largest range, the largest horizontal range achieved by a projectile, as in like the time that it will go the farthest. So horizontal range is how far it goes away from its starting point horizontally. So the largest horizontal range occurs when the angle of projection is 45 degrees. Right, that kind of makes sense intuitively. If you shoot something at like 3 degrees, it's right above the ground, it's going to hit the ground pretty quickly. And if you shoot something at like, 85 degrees, almost directly up, it's going to go up and then kind of come back down again without really going that far. If you're shooting something at 45 degrees, it's like a good medium. It's right in the middle, and that's when it will go the farthest. So if you're ever asked a question on that, or if you're focusing on that for your student experiment assignment, that might be something that's helpful to you. All right, let's move on to the next question. So now we need to calculate the time of flight of the arrow. So, to calculate the time of flight of the arrow, we need to use our equations and formulas. So what I'm actually going to do is I'm actually going to take a snip of those formulas and I'm going to show you my thought process to show what formulas I'm going to use, because a lot of the issues that students come across when they're going through these projectile motion questions is kind of struggling to know which one of the formulas that they should use, especially when you're getting into more of the complex questions. Alright, so it's kind of difficult, especially when on the formula sheet there are so many formulas that you can use. It's kind of a bit scary, I guess. and a lot of students don't necessarily know which one to use. So what I'll do is I'll take you guys through my thought process for which formulas I'm going to use. As I said, especially when you get into the more complex questions, it can be a little bit trickier to know. So here are the formulas. This is just taken directly from your formula sheet. So this is exactly what you'll see when you go into an exam. So let's have a look back at our question. So we want to calculate the time of flight of the arrow. All right. So let's have a quick think first. The time of flight. What is that? The time of flight is going to be how long it takes for the arrow from when it leaves the ground to when it hits the ground again. So in other words, the time of flight, all right, the time of flight will be, and make sure you remember this because this comes up a lot, the time of flight is when the displacement, remember S is displacement, when the displacement in the y direction, the vertical displacement equals 0. So think about it like this. If this is our ground, this is our projectile, the vertical displacement is basically just like the height of where the projectile is. When it's on the ground, the vertical displacement equals 0. The time of flight is going to be in between these two values when the vertical displacement is equal to 0. Something to keep in mind though is this is not always true. This what we've just written here. The reason I say that is because sometimes you have a projectile, say, instead of being projected just along the ground, is projected off a cliff, like this. Alright, so say we have a 10-meter high cliff. In this case, and it hits, say, the ground down here, the time of flight will be when the vertical displacement is equal to -10. So this is really important to understand the difference between. If you have a flat surface like we do in this example here, where the ball or the projectile is just being thrown along the flat surface, the time of flight will be when the vertical displacement equals 0. However, if you have a situation where there's like a cliff or like something being thrown like, onto a fence or onto a table or, something like that, the time of flight will be different. It won't be when the vertical displacement equals 0. So all you need to do is think about how high will the ball be when it hits the ground or the water or whatever. All right? And if you have a 10-meter high cliff, just as a random example, when the ball or the projectile hits the water, the vertical displacement will be -10. It's important that it's -10 because it is lower, the ball is lower than it was to begin with, and that's why it's negative. Alright, if there was another cliff up here, which was 12 meters tall, and the ball was projected between them, like this, then the vertical displacement would be 2. +2, because that is how far it has traveled. Alright, so my point is just keep in mind when you're doing these questions, it's not always the case that the time of flight occurs when the vertical displacement equals 0. You need to kind of keep your wits about you, read the question, and see what's happening in that context. Alright, so we know the time of flight is the time when the vertical displacement is 0. So the only formula that we have including vertical displacement is this one here. Now we don't actually know anything else about when the time of flight will occur. We don't know anything about the final velocity. We don't know anything about the range, the horizontal range, or anything like that, so we can't actually use any of the other equations. Alright, typically when you're figuring out the time of flight, you'll be looking at the vertical displacement. So let's sub our values into this formula. We know that it's y equals 0. We're going to have half g is -9.8. Remember, gravity is decelerating, so that you need to have a negative outside of your 9.8, right? T squared plus uy, so uy was 28t. Now, as you can see, we can solve the equation from here. So if we take that 28 over to the other side, no, sorry, we don't even need to do that. What we'll do first is we'll factorize out the t. Now, this is a really important thing to do when you're solving one of these equations without a calculator. If you have a graphics calculator, you can go in and solve this in EQUA. And you'll just get your answers. But if you're solving it by hand for whatever reason, you need to make sure that you factorize out the t here. Alright, because then if we use our null factor theorem, we'll get that t equals 0 and negative 4.9t plus 28 equals 0. So the reason it's so important to factorize is because otherwise you kind of miss out on that solution of t being 0, and sometimes that is important. So solving this, we get a value of 5.7 seconds. So just having a look at that factorizing null factor theorem bit, if you're a little bit confused about that, I don't really have the time to go through it today, but make sure you ask a friend who's in methods or your teacher. But in all honesty, you can typically just kind of solve these using your calculator or your graphics calculator. Hopefully you have one. And you don't need to worry too much about the algebra of anything. So this tells us that the ball is on the ground at 0 seconds, which makes sense because that's where it starts, and also after 5.7 seconds. So the time of flight is 5.7 seconds. Now let's get on to the next part of the question. So in this part of the question, we need to calculate the maximum height of the arrow. So this is something that's important for you to remember as well. All right? When does the maximum height of the arrow occur? When does the maximum height of the arrow occur? So, this is a really, really important principle that you need to remember. The maximum height occurs when the velocity in the y direction is equal to 0. So the maximum height occurs when the velocity in the y direction is equal to 0. And that's really, really important for you to remember. That's a really common question to be asked, and it's nowhere in your formula sheet. Alright, maximum height occurs when the velocity in the y direction is equal to 0. So, why is this? Alright, why is the maximum height when the velocity in the y direction equals 0? Think about it like this. Say we have a projectile, right? This is the ground, this is the projectile. Where does the maximum height occur? Just like visually, right? It occurs here. That's when it's the maximum height. So, think about it like this now. On the left-hand side, when it's being projected, the projectile is kind of going up, up, up. It's going like more up at the beginning, it's kind of like steeper, but then as it's getting to the top, it's like flattening out a little bit. So those arrows are getting smaller. Then it kind of gets up to the top, gets to its maximum height, then it turns around, and now it's coming back down again. So we have little arrows because it's still a little bit flat, but then bigger and bigger as it's kind of speeding up. So, these arrows represent the velocity and the y direction, right? How fast is it going kind of like vertically? What you'll notice is that at our circle, we're right in the middle. It's in between when that upwards arrow is really small and when that downwards arrow is really small, and kind of at that point at the maximum height, it's actually turning around. To think about it intuitively, kind of think about having a ball and then throwing it straight upwards, right? Straight upwards above you. You kind of watch it rise, getting up and up, up, and then just for a moment when it gets right to the top, it kind of stays still just for an instant, and then it comes back down again. So right at that instance where it's staying still right at the top, right, that's when the velocity in the y direction is equal to 0, because it's turning around. So, to solve this question D, to calculate the maximum height of the arrow, we need to let Vy equal 0. So, let's kind of go down in a list. So for this one here, we can let Vy equal 0. Now we know the other information in this equation, so this will help us, alright? So we can go 0 equals negative 9.8 t, uy was 28. So solving this, we get that t is equal to 28 divided by 9.8, which is 2.86. Something else you might have realized is that because our projectile is just going along the ground, we could have actually just halved our time of flight to get the same answer. Anyway, we know the maximum height occurs after 2.86 seconds. Now, height, remember, is essentially the displacement in the y direction. So we can substitute this time in. So we're going to have Sy equals negative 4.9, that's half times 9.8, times 2.86 squared. Uy was 28 times 2.86. And let's see what this gets us. This gives us an answer of 40 meters. Alright, so that's the maximum height of the arrow. Next, we need to look at the horizontal range of the arrow. So the horizontal range is what we denote as Sx. So that's this formula here. Alright. So Sx is equal to Uxt. So Ux is 28, and the horizontal range of the arrow, so what time will we be using? Well, we'll be using the time of flight, because think about it, the horizontal range is when how far the ball has traveled, so the arrow has traveled when it lands on the ground. So when it lands on the ground is after the time of flight. So the time of flight was 5.7 seconds. Which gives us an answer of 159.6 meters. And that is the end of our question. Alrighty, let's move on to our next topic, which is inclined planes.